Today we're going to do section 7.1. First, let's look at the book. Here we are. This is the page that's supposed to be already scanned, but I don't think I scanned the new part last time. So here's the new part. Let me line it up. Why is it not parallel? I don't know. Maybe like this. Does that look better? Good enough. Something like that. Next, let's look at page 218 and 219. Okay, something like that. And then a bit closer. And on the bottom. Okay. And next, page 220 and 221, which is about like that. Okay, a little closer on top. And a bit closer on the bottom. That should be it. And finally, page 222 and 223. Like that. And then a little closer on top. And a little closer on the bottom. Okay, that should do it. So now let's start on page 217, 7.1. Please read the introductory paragraph yourself, where it talks about the line and surface integrals, which we've already had in Calculus 3. But we are going to redefine and rebuild everything here. Okay, and so first let's consider the bottom of the page. What is a curve? A curve is just a set of points that will define it parametrically as x equal to phi t and y equal to psi t. And psi t goes from A, and t goes from A to B, including both ends. Okay, we're considering curves that closed curves, but they're just a piece. Right, so then let's turn to the next page, where phi is continuous and psi is also continuous from A all the way up to B. That is continuous all the way up to the edge. Let's not do anything about going to infinity or some such thing on the edges. Okay, it continues all the way to the end and the front. Now the next thing is, if phi A equals phi B and psi A equals to psi B, in other words, they come to the same point. Okay, the end and the beginning are the same. If that is the case, then this curve is closed, like a circle, rectangle. Okay, those are examples of closed curves, and it is called a Jordan curve if it is closed and has no double points. Double points is when the curve crossed itself or touched itself at some point and keep going. So then, like the figure 8, for example, so it is a Jordan curve if it doesn't do that. Okay, so then the curve is just like a rectangle or a sphere or something. As long as it doesn't cross itself or reaches that it has no double points, it is called a Jordan curve. No double points means that no two distinct values in t yields the same point, x, y, well, except for the endpoints, right? Because it's defined as being closed. So anything that's not the endpoint do not share points. And then such a curve will divide the plane into two parts, an exterior and an interior. That is a point about in advanced, that will be proven in advanced mathematics, I think in topology, and that you might be interested in after taking this course that you can consider taking. Okay, and I am also planning on teaching topology after I'm done with this stuff. Okay, but one thing at a time. So now, such a closed curve will have an exterior or an interior. This might seem obvious, but sometimes it isn't, because because some curves are so packed together that it doesn't have an interior. For example, if you consider such a thing as a space filling curve, the curve is well, it's so messed up, or so squeezed together that it actually fill up the entire square. Okay, that is, by the time you're done drawing and you look at it, every point of the square that you can find is the curve hits it. Even though a curve it's like coloring, except coloring you have to have thickness to be able to color. A curve has no thickness, but even then is able to fill up space. Again, I believe that was taught in topology and maybe in real analysis. I don't remember for sure. But I will be teaching those courses, okay, God willing, if I don't give up first, that is. But in the meantime, we don't care about that much. But since the book mentions it, I also want to talk about it's an interesting point that you imagine a curve that is so dense that is so packed together that it doesn't have an interior, okay, because it filled up the entire space of, say, a square or something like that. So let's now move on to definition 1, which is what is about regular? A curve is regular if it has no double points, all right, and if the interval AB, and the book doesn't say this, but please make sure you mark that this AB is referring to the closed interval AB, not the open. See, it uses parentheses, and usually parentheses indicate open interval. It doesn't say open or closed, but since we've been talking about the closed interval, right? I mean, from A to B, so I'm going to assume that the book means closed, because if it means open, it doesn't make any sense later. So this AB, it means the closed interval AB, that is including the endpoints. And so what about the interval? The interval can be divided into a finite number of subintervals, also closed, in each of which phi of t is C1 and psi of t is C1. By that I mean it is C1 all the way up to the endpoints. Okay, its derivative doesn't go to infinity or go nuts or anything. Okay, the derivative also politely is continuous all the way up to the end. And another requirement is that the phi prime and psi prime are not both 0 at any given t. And that way, the purpose of that is so that we can calculate the tangent of the thing. Now, if phi prime and psi prime are both 0 at some point, then what we can do is use that point as a new subdivision. That is, we can just stop right there, right? And that is another subinterval. So that interval becomes 2 subintervals, and such that we can continue with this definition. So if psi prime t and phi prime t are both 0 all the time, then I don't know what that is that you're doing. But anyway, it should have only a finite number. A finite number it can be a large number. You know, you can have a billion of them, just as long as it's finite. So next, let's see that it is clear from elementary calculus such a curve is sectionally smooth. Smooth means it has a continuous derivative, or just a derivative. It makes it somewhat smooth, right? And more differentiable from mathematical sense, we consider it more smooth. But that doesn't necessarily translate into the regular sense of how smooth something is. But we just imagine it as the more differentiable something is, the more smooth it is. As a result, the straight line is infinitely anything that's infinitely differentiable, then is infinitely smooth. Okay, most functions we know are infinitely differentiable in most areas. Okay, except when something goes to infinity or 0 or something like that. But anyway, so this thing is sectionally smooth, except for the points where it has corners. Okay, and since phi prime t and psi prime t do not vanish simultaneously, the quotient determines the direction of the tangent. All right, and then the curve may have corners. For example, like if you consider a rectangle, excuse me, a rectangle will be a regular curve. It has corners, but otherwise everything is regular. a Jordan curve can fail to be regular, okay, if it contains a piece of the curve y equal to x sine 1 over x near the origin. Now that is, what is that graph? I plotted it right here. See, here's an example of something that isn't a Jordan curve. The red thing is let's see, the red thing, as you can see, is plotted as t as x sine 1 over x, or in parametric form this is plotted as t and t sine 1 over t, and this thing is not differentiable at 0, okay, at the origin it's not differentiable, and as we mentioned before, the to be regular, the function is derivative has to be differentiable all the way up to the endpoints. So, and which is why I mentioned earlier that the interval had better be a closed interval. Otherwise, this definition will not work out. So as long as that is the case, as you can see, then there's much wiggling going on. Okay, too much wiggling, so it makes it not regular. This thing just it wiggles, and then the derivative then totally go nuts when it approaches 0. Okay, and so the function itself, however, is continuous at 0. That because because the value of the function approaches 0 at 0. So then it is considered a continuous function. It just barely, because it wiggles so much. Okay, towards the end there, it just but it does approach 0. So we have to admit that it is continuous. So this thing is so as a result, this would not be a regular Jordan curve. It is a Jordan curve though, because it satisfies the Jordan curve requirements, which is the endpoint connects to the beginning point, and what was the other one? Oh yeah, there's no double points, so nothing's doubling, right? It just wiggles too much. If you zoom into the origin, it will always look like what you see right now. No matter how much you zoom in, it just continues to wiggle so much that you can't see close to the origin. So that is an example of the non-regular Jordan curve. I should mention that a regular curve will have arc length. That's because it's C1 and it all the way to the end, so and the endpoint. So there's no trouble with just integrating the thing, okay? And because the integral integrating the derivatives squared, which gives the arc length. That's the formula for the arc length. And so next, let's look at definition 2. A region is regular if it's bounded and closed, and if its boundary consists of a finite number of regular Jordan curves which have no points in common with each other. Okay, so remember, Jordan curve is already closed. Now, so why would you might wonder, why would a boundary have more than one Jordan curve, right? Because a rectangle, for example, just have its boundary is just a regular Jordan curve, and the Jordan curves cannot have any points in common with each other. Well, this is an example right here. Okay, when you have your object has a hole in it, so the hole has to have its own boundary that doesn't intersect the outside boundary at all. So, and such a region will be regular. That is, if the boundary actually, if you move the inside hole over so they actually touch the outside boundary, then by this definition, it is not a regular region, because it doesn't want it. The Jordan curves can have no points in common with each other. Okay, stay away. So what this means. So as an example, let's consider the set of point xy for which x1 less than or equal to x squared plus y squared less than or equal to 4, which is this thing I've drawn right here. So it has two Jordan curves as boundaries, and the boundaries don't intersect each other. Now, if we take some points away from this thing, like for example, if we take away the points on the x-axis on the interval x between 1 and 2, so we take away these points. So there's a thin line missing here, okay? But not the border. The border is still there because it says from x, and x is bigger than 1 and less than 2, and not equal. If we did that, then it's not closed anymore, and therefore it is not considered, it is no longer regular. All right. And now, and any region R of previous chapter and is also can be considered a regular region if its boundaries are regular curves. That's we're talking about the last chapter when we had the R of x equal to something, right? Or R of y. Here's an example of that. This is just from previous chapter. However, what an Rx might look like, R of y is similar, but that such a thing would be regular if the boundaries are regular curves. Now this example, this thing is not regular, as we've seen a little bit earlier. So therefore, this is not this thing itself. This is not a regular region. But if the phi and psi functions of the R is regular, or what is it? Well, anyway, if they're regular, then the region will be considered regular, that sort of thing. There's some, so please read this yourself, okay? And just a bunch of minor details that are nevertheless interesting to consider. So next, let's consider subsection 1.2, the definition of line integrals. Now, for a line integral, we will consider a function f xy, which is defined on every point of the curve that we were talking about, which we'll call the curve gamma, capital Gamma, okay? And then I seem to remember that my professors used to pronounce this thing as tau. I must be mistaken. So you still might catch me calling this thing tau. It's gamma. That's the capital Gamma, okay? This, yeah. Anyway, it's the capital Gamma. I looked. So anyway. So then we're going to define the line integral as always. Make a subdivision of the interval a to b by the points t0 to tn. And then if we do that, we'll have two kinds of line integrals. So the integral of a function over that line, gamma, will be as defined as from x0, y0, that's the beginning point, all the way to x1, y1, the end point of fxy dx. And that itself is defined by this limit, okay? We'll take the function of this value times dx will be defined as phi of t and 1 point minus phi of t at the previous t, and for dy is defined the same way. But then we have two different line integrals, one in the direction of x, one not in the direction. One is dx and the other one is dy. And then and that their definition also distinguishes that the one with dy, then we calculate difference and the limit calculate the difference of phi's, and dx we calculate the difference of psi's. So then is and as a result, both these notations might be missing. Like if you integrate over something like gamma, which direction are we integrating? Or if you say if we talk about this thing, then which one is the line? This definition doesn't even indicate the line. But most of the time when we talk about the integral, we'll also specify, for example, if we use the gamma notation, we'll specify which way the line is going, okay? So most of the time we don't have a problem with this. And then the line integral, well, this integral is defined this way, assuming the limits exist, of course. The integrals are, if you compare this definition to page 151, you will notice that this is actually, these definitions are exactly this thing, okay? So I will show you page 151. Not that it's critical, but since the book mentioned it, we might as well look at it. See, on page 151, the Stilger's integral is defined exactly like that, right? D alpha x is alpha xk minus alpha xk minus 1. And just a quick refreshment of the Stilger's integral, but we're not going to go too much into it. So let's move on to the next point. Next, let's talk about theorem 1 on page 219. We have the existence of the line integral. Now, if tau is a regular curve, and regular means it has no double points, and if the interval can be divided at most into a finite number of subintervals where phi and psi are both C1, okay? And phi and psi they are not both 0 at the same time. That's by definition 1 of the previous page. So that tau is a regular curve, so it's pretty decent, right? And then f is continuous. That's not as decent, but we don't care. And then so if that is the case, then the line integral as defined on top of this page, integral of gamma of f dx and then dy, both exist. Now to prove that, first let's imagine that phi and psi are continuous on the entire curve. A curve gamma. If it isn't, we'll just do a little bit at a time, okay, prove a little bit at a time, each chunk, and then add it up. It's finite, so it is at most allowed to be a finite bunch of stuff that's put together, continuous stuff that's put together, and that is phi and psi are both C1. Then we'll pull out the law of the mean, which I will not show you because we've been doing that a lot lately, right? So by the law of the mean, we'll yank something out. What are we yanking out? From the definition up here, we're going to yank out the phi, okay? There's a 5t minus 5t I minus 1. So we're going to yank out phi prime out of here, right? Phi prime, and then they end up having just ti minus 1. And that's from the first law of the mean we learned. So and that's because somebody is differentiable, okay? Because 5t is differentiable, so we can do that. And then a similar thing is done by the psi of t for the dy version. But anyway, where t is, t prime is somewhere in the between the endpoints. So then next we're going to pull out the Duhamel's theorem right there. And Duhamel's theorem on page 173 says that if we have this situation, okay, and then this, if we have a proper situation, then this integral, this limit exists, and it equals to this integral, okay? And in this case, for our case, our alpha x is just x, or just t. And so everything checks out by the Duhamel's theorem, and therefore we have, we're done, because we are just trying to prove that this thing exists. So the Duhamel's theorem hit it with one strike. Now, this integral, as we have seen from the Duhamel's theorem, that is equal to, which was defined on the Stieltjes integral, but that is can be easily considered as, well, anyways, the details can be considered that by it, they are equal to, this thing is also equal to the line integrals by the, are equal to Riemann integrals, okay? And that is on page 156. Let's see, where is 156? Let me get it here for you. I have it bookmarked here, but my bookmark got stuck. 156, right here, right. That's that good old thing here, okay? That is the d alpha is the d alpha x is the same as fx alpha prime x dx. So that is some old rule we have on, this is on page 156. All right, so that is, and as a result of that, we can rewrite this integral as this thing right here, okay? That this sum exists and it equals to this. And where we have the first one, the dx one equals to phi prime t dt, and then dy is psi prime t dt. Okay, so that is the end of the proof of theorem 1. But we have some comments to make, okay, at the bottom of the page that says that we can relax the requirement of tau being a regular curve. For example, we can change it such that the curve tau is maybe not particularly regular, but is monotonic in the sense that phi and psi are both monotonic functions. That monotonic means non-decreasing or non-increasing, okay, the pointing up or pointing down business. So if they are both monotonic, then by the Stieltjes integral theorem on page 152, we have the functions then equal to the Stieltjes integral. That is, they are defined anyway. Okay, with the gamma, the curve gamma being not as restrictive. That is, that it's not necessarily regular, it is only monotonic. We can still define it as Stieltjes integral by theorem 1 of chapter 5, which is on page 152, which I have marked right here. Where is it? Right here. The existence of the Stieltjes integral, which just says that if alpha x is increasing, monotonic, like they say, then this integral exists. All right. So that is that's that. And then another thing we should mention is that if we set phi of t equal to t in this formula here, that is our formula that we derive from here. Okay, this thing. If we just set the phi of t equals to just t, okay, imagine phi of t becomes t, then phi prime t dt is also just dt. Then we will have, and then psi of t belong to c instead of c1. And so we're relaxing the requirement of psi of t. Then we can plug things in and realize that this integral also works. Okay, that is the integral fx dx. If you set phi of t equals to t, then let's see, this equals to f psi 5x dx, and I have it written out in more detail. So see, like this story right here. I have the book copied here. Let's say this is first situation. Okay, over there is the y situation, but let's focus on the x situation here, where we set phi of t equals to t, and then let's say the psi of t is only continuous, it's not c1. Then this thing still works because we can get it from the previous equation. Yeah, I typed this thing here, but in reality, this would have worked better. And what I mean is, I should have had maybe this thing would make better sense. Well, either way, the point is from here we can. Maybe I should fix it. Let me think. Nah, we'll just from here. Okay, we're changing phi of t equals to t, and then and psi of t is continuous. Then we get this equation in the substitution here, as you can. As you can see, I think I'll fix this thing. Nah, it's good enough. Let's not be too picky here. The point is that if we do this, okay, what we're doing is that then this equation, then it will be transformed to this. However, that's because we changed tau, okay? Tau used to be phi of t psi of t in the previous equations, right? If we set phi of t to be just t, then we changed it to a different, did I say tau? I mean gamma, okay? The previous gamma, that is the curve, used to be this curve, and now we're restricting the one coordinate. We just knocked phi of t to be just t. So then that's a different curve, right? And for this new curve, which is, we call it gamma 1, which consists of t comma psi of t. Now for this new curve, then this equation holds. That is, this is being integrated on a new curve, gamma 1. And so once you plug in phi of t is t, then you get this equation, okay, when dx becomes dt and stuff. And then the next step, we're going to change the dummy integration variable into x. So then we got this equation, which will come in handy later. Now similarly, on the other side, we do the same thing except with psi of t, and we got so we get yet another curve, okay, we'll call it gamma 2, which is phi of t comma t, which is different from gamma, notice, because gamma is phi of t psi of t. So this is phi of t t. And now on this new curve, gamma 2, then f of dy is going to be equal to this integral, which will also come in handy later at some point. So now to emphasize the fact that these gammas are not the same. Now the book draw them to be all the same, right? I mean the book says, oh, if we put phi of t equal to t, then this integral exists, which is true, but it uses the same gamma. See, but that shouldn't be the same gamma because this gamma is defined as phi of t psi of t, whereas the new gamma is has phi of t equal to t. So I feel that to be very, very clear, we should call it a different gamma. So that's why I call it gamma 1. And to emphasize the point, I draw a sample here. Now take a look at this. This is the original gamma, okay? I made up gamma equals to phi of t psi of t. I made up a quick example here and drew the gamma right here. So gamma is that curve, as you can see. And then if we set phi of t equal to t, then the new gamma, which has the same old psi of t, that both in my example is sine 3t, but the gamma 1 doesn't look quite the same, right? Because it's somewhat different from gamma. And then the other option where we set phi of t equal to t, I plotted that. It looks still different because now the gamma 2 is just phi of tt, okay? So which is different from the original gamma. So I just want to be clear on this. So these equations, in other words, these equations work, but under the strict condition that this one only applies when phi of t is t, and that one only applies when psi of t is t, okay? To make sense compared to what it used to be before. So that is that's that. And so the next thing is, all right, so then now that we've done this, there is a quick comment here in the book that says we can do the line integral around the whole boundary of an Rx or an Ry. That is, the one that's doing dx can, let's see, the equation, well, the one that does, well, whatever. The point is then being that our lines are along the regions, then it is possible to do integration along those various lines. And we'll think about this more in detail later. But for now, just that is something we can bear in mind, that this definition allows us to do certain line integrals and their existence. So that is that. So the next point, the book has 3 examples. Please do them yourself. They're very straightforward, similar to what was done in basic calculus, okay? And when we first learned about line and surface integrals. So please do those yourself. And I have also done them right here. Okay, where to go? Right here. All right, so there's I believe that's example A, B, and C. As you can see, it didn't take that much space to do that stuff. Okay, so that should be that. So I will continue this video, this section in the next video.